So I'd like to thank the organizers. This workshop has been really great so far. Learned a lot. It's been a very broad array of talks, so it's been very interesting. So my name is Joakim. I'm a postdoc with Amit Singer's group at Princeton. And I'm going to present some work that I've been doing together with Amit and Tejal, who is a graduate student there. So I think most of you are familiar with PCA, right? We have a bunch of data points. We want to characterize the mean and the covariance of those data points. This tells us a lot about the data. This tells us how they're distributed and what the principal directions of variability are that we might care about if we want to compress or if we want to do some sort of processing of this. It can tell us a lot of information. That's what we would want to do in the standard PCA case. But we don't always have access to these underlying data points. Sometimes we have observations that we get through these linear mappings, AK, AL, that can vary. It could depend on the data point. We have one different one for each K. And then we have corruption by noise. So we have only access to these observations here, and we want to use those to, again, estimate the mean, estimate the covariance of the underlying data points. So this is the model that we're going to be considering here. And one reason that we want to do this is, for example, in cryo-EM. And so you already heard some about this yesterday in Abbas's talk. I'm just going to go through it a little briefly here. So the idea is that we have these molecules that are frozen in very thin ice. We bombard them with electrons, and we get these projection images. From the projection images, we want to reconstruct the original molecules. And the model that we use for this is we have essentially a linear model. We have our density that's from the molecules, and we have a projection in some random direction, and we have a filtering due to point spread function of the microscope, and then finally noise. So this is the type of linear model that actually describes pretty accurately what happens in the microscope. So again, what we observe are these linear measurements of the underlying data. We don't have access to the underlying molecules, but that's often what we care about in the end. So one of the things that we might want to do here is we might want to denoise the images. Say we want to find if we have outliers or if we want to find the relative rotations between the different images. This is something that we would want to do. And so essentially we want to invert this bandpass filter, and we want to reduce the noise. And if we have our original projection image here, what this essentially looks like is we have this bandpass filter which is going to reduce the low frequencies, reduce the high frequencies. It's going to set some frequencies to 0, and then we have this very high noise that corrupts our data. SNR is typically around 0.1, and so that's something that we should be, we need to be able to deal with, essentially. So we can't do this the naive way. We can't just invert this because the bandpass filter is going to have lots of zeros, it's going to be ill-conditioned, and it's going to cause us problems. So we can't invert this directly to get at the original clean projection image. But often what's going to happen is that our data is going to lie in some low-dimensional space. The covariance structure of the clean projection images is going to be low rank. So if we can find this low-dimensional space by looking at the top eigenvectors, then we can invert the bandpass filter on that low-dimensional space. So if we have access to the covariance structure of the data, this tells us a lot about what we can do to invert this operator. One other task that we're interested in is heterogeneity. If we have molecules that can exist in different states, then we often want to classify the projections of those molecules prior to reconstructing them so we can see the different molecular structure that a particular protein or enzyme can take on, for example. And this is, again, related to what Abbas was talking about yesterday. And so here we have two images that are from two different classes of the same data set. So they're both ribosomes, but they exist in slightly different conformations. And so if we compare this with, if we reconstruct these after clustering and so on and reproject the images, this is what it looks like. So they're already very similar. There's some differences here in the top right corner and in the bottom left corner, but they're already pretty similar. And then we add all of this noise, so you can imagine this is quite a difficult task. But it turns out that if we know something about the variability of the molecules, we can classify these images pretty easily. So again, formalizing this, we have the images that we observe, the y vectors, and we want to classify the y vectors according to the state of the underlying molecule. And again, we can't invert these linear operators directly because here it's even worse. It's something that goes from a higher dimensional space to a lower dimensional space, so we don't have any hope of inverting this without having some additional information. But again, these volumes are often going to live in a low dimensional space. For example, if we only have 2 molecular structures, these are going to live in a linear space. And if we can find that, then we can have some hope of inverting these linear operators. And once we have that, we can cluster, we can reconstruct, and we can do all these things that we'd like to do if we can take advantage of this low dimensional structure. Now, in both the denoising case and in the heterogeneity case, what we're doing is essentially we have these very noisy projections, but because we have a lot of them, we're able to aggregate them, and we get accurate estimates of these mean and covariance statistics, and that's what lets us then do some further processing of the images. And I should say also that this approach of restricting to a low-dimensional space by finding the covariance is something that came from original ideas by Pavel Penček's lab. The difference being that they had an algorithm for estimating the covariance structure that was a little more heuristic, and so we provide some more guarantees for the covariance estimation. All right, so how do we estimate these things? Well, if we just look at the mean, we have these observation vectors for a fixed k, and we look at the expectations of those. Now, the expectation of that is going to be related quite simply to the expectation of the underlying data points by just multiplying with the sensing matrix AK. So we'd like to solve these equations that we have for the different k's. Unfortunately, we don't have the left-hand side. We don't have the expectation for the observation vector. But what we do is we just have that single observation vector. And that's an unbiased estimator for the expectation. It's a very high variance one, but it's an unbiased estimator. So we set these two equal, and we say that on average, we want these to be relatively close. And if we do this for a lot of images, we get this least squares objective that we can optimize to find a mean data point. And we can do the same thing for the covariance matrix. If we look at the covariance for a specific k, we fix an observation matrix AK, and we look at the covariance matrix for this. And what happens is that the covariance matrix of the observation is going to be related to the covariance matrix of the underlying data plus a noise term that we have. So we'd like to solve something similar for this. But we don't have the actual covariance matrix, so we estimate it with just taking the outer product of the mean-centered observation vector. And we put these together, and we get another least squares estimator. This one is a little bit more hairy, but it's a similar idea, right? And we can solve this to get an estimate of the covariance matrix for the underlying data. Now, to actually calculate these, what we want to do is we want to differentiate, set to 0, so we get normal equations. This is all pretty standard stuff. And for the mean estimator, this is fine. We get this matrix. We can calculate it. We can invert it in most cases. For the covariance matrix, it's slightly trickier, but it's the same idea. The difference here is that the operator ln that's in our left-hand side is something that takes a matrix of size p by p to another matrix of size p by p. So if we were to write this out as a matrix, it would be p squared by p squared. So these things are pretty big, and often p is going to be in the hundreds or in the thousands. So we can't really calculate this explicitly. Instead, we have to resort to iterative methods for solving this, like conjugate gradient. And we can do this pretty efficiently because we have a simple way of describing the ln operator as these matrix multiplications. So this is something that we can do. And it turns out that for specific structures, for specific problems, we can actually make this a lot faster by using some computational tricks. I should also note that the right-hand side here is essentially a sample covariance of the back projected observations. So we take the observations, we put them back into the underlying X space using just a transpose, and then we take the sample covariance. So what ln is doing is it's taking that sample covariance, and it's in a sense rescaling it so that we get a proper sample covariance for the underlying data. Now, these have some nice properties. For example, if we set the sensing matrices to be just the identity, we recover the normal sample mean and the sample covariance matrix. So that's reassuring. We're getting something familiar here. Another thing is that we don't have to assume much about the distribution of X. This just comes from just having a random variable. We have i.i.d. samples. That's all we really require. If we do have some additional information on the X's, this is something that we can add in our least squares objective. We can add some regularizer, and it's pretty flexible in that way. And finally, most importantly, we have some consistent results for both the mean and the covariance estimator. As n goes to infinity, we're able to recover the expectation and the covariance pretty accurately. And these are results from Jean Katsevich and Amit's paper from 2015. Now, this all works pretty well if we have a data set where the dimension is pretty small with respect to the number of data points. Unfortunately, in cryo-EM and a lot of other applications, the dimensionality of the data set, like I said, you can have p in the thousands and n may be in the 10,000s or something. So these are almost comparable quantities, right? You don't have n much, much larger than p. And that means that we get into some issues when we're estimating sample covariance matrices. And that's true for the classical case, that's true for our case as well. So to just give you an idea of what happens, if we have the observations are just pure noise, and we try to estimate the covariance matrix using the sample covariance. In the case of n much larger than p, we get classical stuff, we get the central limit theorem, and everything converges around the single eigenvalue of the covariance matrix. If we have n comparable to p, we get what's called the Marčenko-Pastur distribution, where the eigenvalues of the sample covariance are not all concentrated into one, instead they're spread out according to this limiting law that's given by Marčenko-Pastur. Now, if we add some signal to this, we get some interesting results. In the case of the central limit theorem, it's pretty straightforward. We just have the signal eigenvalue here. X is just a rank 1, has just a rank 1 covariance. That eigenvalue is just shifted by 1, or by whatever the variance of the noise is. So we can subtract that out and get a good estimate of the signal covariance matrix. In the case of n comparable to p, this is called the spike covariance model. We get that the spectrum contains this noise distribution, this bulk noise distribution, plus a little bit of the signal. And this depends on how strong the signal is. If the SNR is lower than this critical threshold given here, then in fact the signal eigenvalue gets absorbed into the bulk noise distribution and we can't observe it. But if it's larger, then it pops out and it turns out we can actually access some of that information. And what we do is fairly intuitive. We apply what's called spectral shrinkage to the sample covariance estimator. And so we have this thing, we have a bulk noise distribution that we don't want. We know it's due to the noise. We can describe it fairly well. And we see we have a signal eigenvalue that pops out. So essentially what we do, we take all of these noise eigenvalues, we set them to 0, and we move the signal eigenvalue down by an appropriate amount. And there's ways to do this in optimal ways. This is a paper from 2013 by Donahoe, Gavish, and Johnstone, where they proved some optimality results for these type of eigenvalue shrinkage methods. So this is a way we can estimate the signal covariance in high dimension. Now, so in our situation, like I was saying, our right-hand side in our covariance estimator system is essentially a sample covariance matrix. And we can see this by considering the clean case. So in the best case, we have no noise, it's all clean. We get this right-hand side here. So it's the sample covariance matrix. And if we take the expectation, we see it's just a sum of these covariance matrices that we get from the individual observations that have been back projected by the A transpose matrix. And if we consider the A matrices, the sensing matrices, to be drawn from some random distribution in an independent way, then this is actually just the covariance matrix of this random variable here, where we take our underlying data point, we project it into the observation space, and then we back project it. So that's the covariance matrix in the ideal case that Bn will tend to. So if we have very large n, we expect Bn to be close to this in the clean case. So this is like the best that we can do. We know that in this case, we get a very good estimate of the covariance matrix. So, but we don't have this. We have noisy data, and how do we estimate this particular covariance matrix from the noisy observations? Well, we can take our noisy observations and we can apply A transpose to them. So then we see that the first term is going to be the signal that we want to use to calculate the covariance matrix, and then we have a noise term right here. The noise is unfortunately not white like in the spiked covariance model, so what we have to do first is we have to calculate we have to approximate its covariance matrix, and we have to apply whitening. So we get these whitened observation vectors. We can form the sample covariance of this. We can apply the spectral shrinkage, and this is something that, again, we know how to do. And then we can unwhiten to get an estimate of the BN. And it turns out this is actually much closer to the clean one than we would have gotten if we had just done the straightforward sample covariance calculation. All right, so like I was saying, we can apply this to different tasks. The two that we've looked at most is the deconvolution task and the heterogeneity classification task. And so this is mainly work done by Tejal. So again, we want to have an estimate of the clean projection image given these noisy filtered projection images where we have this point spread function that kind of ruins what we have. So again, we can use this covariance matrix estimation to get an idea of what the directions of variability of the underlying clean projection images are. And so there's a lot of computational details that go into actually solving the system because it can be very large and you run into a lot of issues with that. But if we do that, we get a good estimate of this covariance matrix, then what we can do is we can form a Wiener filter, a generalized Wiener filter that basically gives us the linear mapping from the YKs that give us something that's closest to the XKs in an expected mean squared error sense. So just using the covariance structure of the noise and the covariance structure of the underlying data, we're able to construct this Wiener filter. Now, first of all, we want to see how well we do in terms of the shrinkage as opposed to not doing the shrinkage. And it turns out that if we compare, this is for different SNRs without shrinkage, and this is for different SNRs with shrinkage. And so we see that we get a much better estimate of the final covariance matrix by applying this shrinkage, just because we are in high dimension, and so we get this Marčenko-Pastur distribution of the noise that we want to get rid of. So this turns out that this is a good idea. If you want to look at some results, here we have some very noisy images from an experimental data set of the TRPV1 protein. And we can use all these 36,000 images. We can estimate the covariance matrix of the clean projection images, construct a Wiener filter, and the denoised result that we get out of this looks something like this. So it's a lot different, obviously. We've reduced a lot of the noise. And again, the reason that we can do this is because we have access to a low-dimensional subspace. The noise lives kind of everywhere in the images, but the actual images that we care about are in such a low-dimensional space that we can actually get access to these pretty well if we know what that space is. And so just to validate, we can compare this to some projections that we get if we actually run the whole reconstruction process, and those look like this. So we get something reasonable out of this. It's not as clean, obviously, as the reconstructed ones, but it shows that this seems to kind of make sense, this filtering. All right. So the other problem that we were talking about is the heterogeneity problem. So in a sense, here we take this one step further. Instead of just considering the measurement matrix as this bandpass filter, we also consider the projection. And we want to classify the images according to the underlying molecular state. Right? So we can use this method, like we're talking about for estimating the covariance, to get an estimate of the covariance of the underlying molecules. And there's some issues here because, again, this matrix is very large, so we want to use conjugate gradient, but it still can take a lot of time because we have to go through the data set each time if we want to apply ln the way it's written. So it turns out we can actually simplify this quite a bit by writing this as a convolution, pre-calculating the kernel, and then applying ln is very fast because we can do it with fast Fourier transforms. And also there's some preconditioning that comes into this to make this converge relatively fast. But once we do all of this, we get a good estimate of the covariance matrix. And this covariance matrix is going to describe to us the space in which the volumes lie, the principal directions of variability. And this is going to be a low-dimensional space. For example, if we have C different molecular states, the covariance matrix is going to be of dimension C-1. So this is going to be a lot smaller than the ambient dimension, and this means that we're able to invert, and we're able to find these coordinates, and we're able to cluster in this particular space. And I should mention that this will also be true to a lesser extent, but this will also be true if we have a manifold structure instead of these discrete classes. If that manifold structure is smooth enough, we can expect to find it in a low-dimensional space. So we can test this on an experimental data set. This is from Joakim Frank's lab, and we have 10,000 images. And so if we estimate the sample covariance, or if we estimate the covariance matrix of these molecules, we see that we have not a super clean estimate. We have these bulk noise distribution down here at the bottom, but we see we have some signal eigenvalues that pop out. So this suggests that we have maybe 1 or 2 dimensions in our space that the molecules will occupy. So if we just look at the top eigenvector, we just look at the one-dimensional space that these are in, and we look at the histogram, we get something like this. If we find the coordinates in this space that best fits the images. And so we have a bimodal distribution, which is expected because, again, this data set, we should have 2 classes in it. This is what people have found with other methods. And if we compare it to the labeling that is given with this data set, which was achieved using a supervised classification scheme, we get around 89% agreement with respect to this labeling. But we're able to do this in about 26 minutes on a standard workstation, whereas these other methods often will take several hours up to a day, depending on the settings that you give it. So we get something that's relatively accurate, and we get this fast, which is nice. I'm also going to show you. Yep. So these are the 2 volumes that we reconstruct if we interpolate between them. So you can kind of see there's a little bit of rotation going on here. There's different things coming into view down here. So there's definitely, they're very similar molecules, but there's definitely some change that we can observe between these two states that we have. All right. And then just finally some conclusions. So this way of estimating the covariance matrix for these linearly reduced measurements with noise, it's a fairly simple model, but it's a fairly simple method rather, but it allows us to do very powerful things. We can get very good estimates by using this least squares estimator for the covariance matrix. And in the case of high dimension, we have some issues, but we can get around those to a certain extent by applying this eigenvalue shrinkage, which seems to work very well. And then finally, for the particular task that we're talking about here, which is deconvolution and classification in cryo-EM, having this covariance matrix information is really helping us out. It's a really powerful way of solving these problems. And then finally, some future things that we're looking at. At least in the cryo-EM case, we expect that there should be some sort of sparsity constraints that the volumes will satisfy. So we'd like to incorporate this to regularize, in a sense, the covariance matrix estimation. So this is something that we're looking at how to do that. Also, like you saw, there's still some noise in the covariance estimator that we kind of understand it qualitatively, but like you saw, we just picked the top eigenvectors and then we forgot about the rest. So it would be nice to have some more principled way of characterizing this noise distribution and being able to set a threshold based on some solid theory. And then finally, we're looking at applying this to other cases where you have variability in underlying data, like embryo development. You have microscope images of fruit fly embryos that are developing, and you want to trace the variability across snapshots. But also MRI imaging, where you may have movement of the patient while you're imaging. This happens a lot with children for some reason. And then finally, matrix completion. You can put this in a similar type of framework. So this is things that we're looking at right now. And these are some papers regarding the covariance estimation for classification, for denoising, and then some theoretical results on these estimators. And that's it. Thank you, guys.